Okay, welcome to Chapter 7, Acids and Bases. So we're well into the course now, and hopefully a familiar topic. I'm sure most of you have at least heard about acids, and maybe those who haven't heard much about bases will get to know a little more about acids and bases here in this chapter. Starting off with our learning objectives, obviously we'll need to distinguish between acids and bases here, and we'll use chemical and physical properties to do so. We'll explain how an acid-base indicator works, and then identify Arrhenius and Bronsted-Lowry acids and bases. We'll note the similarities and differences between those two definitions of acid and base chemistry. We'll write a balanced equation for a neutralization or an ionization reaction. And we'll identify acidic and basic anhydrides and write equations showing their reactions with water. We'll move on to define and identify strong and weak acids and bases, and I'll give you some hints as to how to tell the strong from the weak. We'll identify the reactants and predict the products in the neutralization reaction. We'll describe the relationship between the pH of a solution and its acidity or basicity. And then we'll find the molar concentration of hydrogen ion, H+, from a pH value or the pH value from the H+ concentration. We can go either way there. Finally, we'll write the formula for the conjugate base of an acid or the conjugate acid of a base according to the Bronsted-Lowry definition. We'll describe the action of a buffer and explain why buffer systems are so important, especially the buffer system in our blood. We'll describe everyday uses of acids and bases and how they affect daily life. We'll recognize carbon dioxide in water as a useful, safe source of acid, a very weak acid, carbonic acid. And finally, we'll describe alternate choices for greener reaction conditions when using acids and bases. Okay, so let's dive into our definition of acids. Before we define them, let's talk about what they do, right? Anyone who's had anything with vinegar in it, think Italian salad dressing for instance, notices that sour taste of the vinegar. That's a characteristic of an acid, and vinegar is a solution, dilute solution of acetic acid. So that sour taste also could be attributed to different acids, citric acid for instance, in citrus fruits. So there's lots of different acids that we encounter. In addition to tasting sour, acids will turn litmus red. Litmus is made from Spanish moss, so those plant components change color to red in the presence of acid. They'll also react with active metals to release hydrogen gas. So I'm sure some of you have YouTubed the Works toilet bowl cleaner and aluminum metal from aluminum foil, and it's a very noticeable gas-forming reaction. It's not a safe one to do. Wouldn't encourage anyone to do it. Actually, I would actively discourage you from doing it, but a number of people have done it and posted those videos. And it generates hydrogen gas in large amounts. Finally, a characteristic of acids is that they react with bases to form water and a salt. Okay, so let's go ahead and define bases in terms of what they do, just like we did for acids. So if you notice, bases have the characteristic of tasting bitter. So if you like bitter greens, that's because of all the bases that are present, the nitrogen-based bases there. Also, if you think about something like a solution of sodium hydrogen carbonate, baking soda, it has that bitter taste. If you use baking soda toothpaste, for instance, and they don't add a lot of extra flavor to it, there's a bitterness to it. Whereas the acids turn litmus red, bases will turn litmus blue. So that's a giveaway there that we're dealing with a base, at least for our course's definition. Bases tend to feel slippery, so if you get a strong base on yourself, or even a weak base like ammonia, if you're cleaning with ammonia, certainly you should be wearing rubber gloves, but if you happen to get a little on your skin, it'll start to feel slippery because the base will start to react with the triglycerides in your skin and make glycerol and fatty acids through that reaction. And finally, just like acids reacting with bases in our last slide, we have bases react with acids to form water and a salt. So we tend to define acids and bases in terms of how we encounter them and what they do with each other in particular. That neutralization reaction is very important for our definition of acid-base chemistry. Alright, now we're looking at some pictures. At the far left, we have some acids, vitamin C, ascorbic acid. We have aspirin as well there, acetyl-salicylic acid. There's, I think, a lemon and an orange, some citrus fruits that have citric acid present. And then we've got our wine vinegar, a little more complex solution than plain old distilled white vinegar, but in either case, they're roughly 5% solutions of acetic acid. If we look at the middle picture, you've got some bases. So bases tend to neutralize acids, which is why that Phillips milk of magnesia is a nice base to take if you've got acid upset stomach. Likewise, baking soda is good for that, or for cleaning, as is ammonia next to it. So cleaners tend to be basic because food stains in particular tend to be acidic. And then finally, we've got the liquid drain opener, and that is a very strong base, potassium or sodium hydroxide, and that's useful for removing hair or grease clogs in drains because the base will react with those substances. Finally, we've got some salts, so you can think acid plus base yields salt plus water. For the kosher table salt, sodium chloride, that's two strong substances, a strong acid and a strong base, and it gives us a nice neutral salt. Epsom salt, magnesium sulfate, heptahydrate, the particular, is slightly basic, and aluminum sulfate is actually somewhat acidic as a salt. So salts aren't always neutral themselves, but they do tend to be the result of acid-base reactions. For the first definition of an acid, we'll talk about Arrhenius' definition here. Svante Arrhenius, the scientist who did a lot of the early work in acid-base chemistry, he defines an acid as a molecular substance that ionizes in aqueous solution to form hydrogen ions. So notice we're dealing just with water here because it's aqueous solution. And so this is the most narrow definition. It's also the one that's the earliest and simplest for us to use. So if you think about the common acids you might have already heard about, things like sulfuric acid or hydrochloric acid, other substances in our table, these tend to be thought of as acids in any definition, but particularly in the Arrhenius definition. And we see there's lots of common uses. Sulfuric acid is battery acid in your lead acid battery in your car, which is present for most cars. Hybrids might have a different battery chemistry, but most traditional cars use sulfuric acid and lead oxide in their components. And you see we've got lots of other types of acids identified and uses for those acids, but sometimes the acids are particularly hazardous. Boric acid there, second from the bottom, is a roach or an ant poison. Hydrocyanic acid, another weak acid, is extremely toxic to humans, and we have to be careful with that one. We would never use it in the course, but in advanced graduate or beyond chemistry courses or labs, you might have to use that substance. Certainly it's used in the plastics industry, as you see there on the list. So lots of great uses for acids, and hopefully a little better understanding that they're giving off those hydrogen ions in aqueous solution according to the Arrhenius theory. Now looking at the Arrhenius theory definition of a base, we've got a substance that produces hydroxide ions in aqueous solution. And if you recall from the acids, they made hydronium ions or hydrogen ions, H+. H plus and OH minus come together to give HOH, or good old H2O. So that's the reason why we said early on, acid plus base yields salt plus water is your characteristic neutralization reaction, because the other substances, the other counter ions, are what form the salt. So if we look here, we've got a number of common substances. We've got the sodium hydroxide and potassium hydroxide. They're both called lye in everyday speak, and either one could be used in a drain cleaner like we saw a couple slides ago. You've got lithium hydroxide used in alkaline storage batteries, and then calcium hydroxide, very important to the cement industry. Magnesium hydroxide, we talked about that as milk of magnesia. It's an antacid and a laxative both. And then ammonia is a nice household cleaner because it's a weak base, and it will remove those food stains that are commonly the problem in cleaning your home. but it does have that characteristic smell. If anyone's ever used ammonia, they know exactly what I'm talking about. Alright, and here we see it again, the neutralization reaction defined for us as an acid reacting with a base. The properties of each are neutralized, so we get something that's roughly neutral anyway, although we'll see there are some exceptions. And also a salt. The salt itself can be somewhat acidic or basic depending on what it's made up of. But our characteristic neutralization reaction is acid plus base yields water plus salt. Since we commonly do our chemistry in 120 here in water, we don't notice that little bit of extra water, but certainly we follow the salt that we produce in the acid and base that we start with. Alright, so we've used the Arrhenius theory to define acids and bases. Now we'll talk a little bit about the limitations here. So one of the big problems is that H plus ions, which if you think back a few chapters, we said that hydrogen has 1 electron and 1 proton in most of its cases. 90-some% of hydrogen is the protium isotope. So when that electron's lost, what we're left with is just the proton, an H plus ion, and they don't exist in aqueous solution by themselves. So what will happen is they'll form what we call a coordinate covalent bond. The hydrogen ion, the proton, will be attracted to a lone pair of a water molecule, and you'll get the hydronium ion, H3O+. And that's not even entirely true either. There's other water molecules that surround it, and they sort of share that H+, so it gets very complicated, and the Arrhenius theory oversimplifies this drastically. It also doesn't explain the basicity of ammonia and other compounds that don't have an OH in their chemical formula, right? NH3, you wouldn't expect that necessarily to be a base according to Arrhenius theory, but what it does in water does permit it to be a base. And then finally, we're limited to water here, which is good for the most part, but when we talk about organic and biochemistry, well, biochemistry is still largely water-based, but organic chemistry is typically not water-based, so there'll be a big section of our course where we don't really want to be in water, and the Arrhenius theory doesn't work outside of water. Okay, so here's another definition. Bronsted-Lowry theory, definition of acid and base chemistry, is a bit broader. So if it fits the Arrhenius, it's going to fit the Bronsted-Lowry definition as well. And Bronsted-Lowry takes us out of water by just calling an acid a proton donor. So we're still stuck with that H plus ion, but we don't have to be in water. Our example here shows water, but it also shows that the HCl gives the H plus to the water and therefore leaves behind a Cl minus. For a Bronsted-Lowry base, you're now a proton acceptor, so you don't need to have OH minus anymore. So NH3 accepts that proton onto one of those lone pairs, the lone pair on the ammonia, a nitrogen atom, and in this case it generates OH minus in water, which technically allows it to fit the Bronsted-Lowry definition, or I'm sorry, the Arrhenius definition, but Bronsted-Lowry is a much broader definition by calling it just a proton acceptor. And here we see the Bronsted-Lowry theory as a picture. You have the acid, which has that proton, that H attached at the extreme right end here, and then there's a base with a lone pair available there at its left end, as we see in the picture, and we get that proton transfer, the H plus going from the acid to the base. So now the acid has the lone pair, and the base has the hydrogen sitting on the lone pair that it had on the left-hand side of the reaction. So we've traded the H plus from the acid to the base. Notice the electrons don't move, just the H plus. So when that proton transfer happens, or more correctly, when the Arrhenius definition, when we have our H plus and OH minus pair, we also get the counter ions. So if we were thinking about something like table salt, NaCl, very cheap and available and important for human health, although not in too big of quantities. So limit your salt, but you don't want to cut it out entirely. If we think about the acid and base that would have reacted, HCl and NaOH would have reacted to form the H2O, the H plus from the HCl and the NaOH from, the OH minus from the NaOH. Those would come together to make the water, and then you have the Cl minus left over from HCl and the Na plus left over from NaOH to make salt, table salt, NaCl. We see a lot of other salts listed here because, as our definition says, salts are ionic compounds composed of cations other than hydrogen and anions other than hydroxide. So if they came from an acid that had an H+, now you've got an anion that's left behind, say Cl- for HCl. In the case of the hydroxides, you have some cation present. Sodium hydroxide, for instance, would have sodium ion, and so on and so forth. So we're just looking at, typically for our course, metal ions and non-metal ions to form. The metal ions would form the cations, and the non-metal ions would form the anions. We see a bunch of those listed here and their uses. So lots of different salts. They don't even list NaCl, the salt that we know the most about, but there's lots of other examples here for you to look at. All right, back in our learning outcomes, we said that we would be able to define an anhydride. And so an anhydride means literally without water, right? So non-metal oxides are examples of acidic anhydrides. And what that means is it's like we took an H2O molecule out. So if we were to add an H2O molecule back in, you see sulfur trioxide, one of the acid rain gases. If that sulfur trioxide reacts with water, it makes our good friend, the strong acid, H2SO4, sulfuric acid. So obviously, if your coal-burning power plants or other sulfur trioxide emitters are not trying to capture that sulfur trioxide gas before it gets out into the environment, then you're going to be contributing greatly to acid rain because the sulfur trioxide will react with water in the atmosphere and make sulfuric acid, which will greatly decrease the pH of the rain and can cause problems to aquatic life and statues like marble statues and various other issues, negative impacts of acid rain. So if nonmetal oxides can give rise to acids because they're acidic anhydrides, metal oxides can often be thought of as basic anhydrides. So if we look at the example here, lime, calcium oxide, reacts with water to form slaked lime, which is calcium hydroxide. And there we see the hydroxide ion that we recognize from the Arrhenius theory definition of a base as being one of the characteristics of a base, right? It has hydroxide ions. So the nonmetal oxide, sulfur trioxide, in our previous slide, when we added water, we got sulfuric acid. Here, when we take calcium oxide, a metal oxide, and add water, we get a base, calcium hydroxide. And you see that process there. At the bottom, we see how the oxide ion specifically can give rise to two hydroxide ions. Okay, so now that you hopefully have a better idea about what acids are, let's talk about how we can distinguish between strong and weak acids. So the big difference is that strong acids ionize completely in water solution, at least the acids according to the Arrhenius definition. So HCl essentially goes all the way to completion to form H+ and Cl- ions. As we already mentioned, there's not truly H+ ions in solution. It's more like H3O+. But for our simple definition, and again, just looking at what we have in the chemical formula, we have no H2Os present, so we just say H+ and Cl-. For the weak acids, they only partially ionize. We see that double-sided arrow to indicate that actually for HCN, most of it stays as molecular HCN. Only a very small amount goes on to make H+ and Cn- ions. So if you know something's an acid, the easy way to distinguish between the strong acids and the weak acids would be to look at the formula. For our course, there's only 6 strong acids: HCl, HBr, HI, HNO3, H2SO4, and HClO4. So those are your 6 strong acids. If it's anything else, it's a weak acid. That's a lot easier to memorize the 6 strong ones than to memorize the thousands and thousands of weak acids that are out there. Okay, likewise, now that I think we have a better idea of what a base is, let's distinguish between strong bases and weak bases. So strong bases, just like strong acids, ionize or dissociate completely in aqueous solution. So NaOH, for instance, gives up its complete Na plus and OH minus ions. If you look at a weak base like ammonia, NH3, it only somewhat dissociates into the NH4 plus and OH minus ion. Most of it stays as NH3, and only a small amount goes on to form the ammonium ion and hydroxide. So like our 6 strong acids, we can talk about 6 strong bases that we'll commonly encounter in the course: NaOH, LiOH, KOH, and then you've got CaOH2, BaOH2, and SrOH2. So those are the 6. And calcium hydroxide, CaOH2, is sort of intermediate, but we'll lump it with the strong bases just to have 6 of those, like our 6 strong acids. Anything else that's a base would be a weak base for our purposes. And here we see another picture showing us that dissociation of NH3 in water to form NH4 plus and OH minus. If you look, the top arrow that shows us going in the forward direction is small, and the bottom arrow showing us going in the reverse direction is longer. That indicates that the preferred direction is to go backward, is to have the NH4 plus and the OH minus react to reform NH3 and H2O. So very little of it goes forward. Most of it stays as the NH3 and H2O. So it shows not only how ammonia acts as a base by accepting a proton from water, but also how most of it stays as neutral ammonia in neutral water. Only very small amounts form the ammonium ion and the hydroxide ions. We've already defined the salts in terms of acid plus base, yielding salt plus water. So let's look at the water part of that. The reaction of an acid and a base is called a neutralization reaction, and if we're looking at what really changes, it's that the H plus and the OH minus, those 2 ions, come together to form neutral water, and that's also in an equilibrium. See the double-sided arrow. So even in a glass of pure water, there's going to be some H plus, or really H3O plus, and OH minus ions. It's a very, very small amount, but it is an equilibrium that exists. Most of it's as molecular as water, but some of it, a very, very small amount, an important number as we'll see, does what we call autoionizes. The water and the ions, the H3O plus and OH minus ions, are all present together. Alright, so during neutralization, the acid and the base react, forming water and a salt. So the water part is what we focused on in the last slide. Here we see that salt, NaCl. Notice the single arrow because it's a strong base and a strong acid, so they really want to react to form that salt and water. And the water itself will go on to form its own equilibrium between H2O and H3O plus and OH minus. One of the classic laboratory exercises in general chemistry is to look at how much acid or base there is in a solution by neutralizing it. So here we see an indicator, something that changes color. We talked about litmus changing to red in acid or to blue in base. Here we see phenolphthalein, which is an indicator that is colorless in acid, and becomes that magenta hot pink color in base. So in part A, we are still mostly acid. We don't see much, if any, of the pink color down where the drops are forming. Most of the solution is clear and colorless because it's still largely acidic. As we go to B, we're starting to see that where the drops of base, which is in the burette that's delivering solution up above, where the base is falling, is showing that it's changing from an acidic to neutral and almost even basic by the time we get to C. So this is a classic way to determine the amount of acid or base in a solution by performing this neutralization reaction in the presence of a visible indicator that tells us when we've gone from, in this case, being acidic to being slightly basic. Alright, so how do we determine numerically if something's acidic or basic? We saw in that previous example we started off acidic and then by the end we were basic. Well, the pH scale allows us to determine when we are acidic, neutral, or basic. So this all applies to water at 25 degrees Celsius, to be very precise about all of this. So that's where pH 7 is neutral. If we're talking about a different temperature or a different solvent other than water, then our numbers change somewhat. But for most cases that we encounter in our course, we're talking about aqueous chemistry, so chemistry in water at room temperature, 25 degrees Celsius. So pH of 7 would be neutral. Anything less than 7 would be acidic, and anything more than 7 would be basic. This is a log scale, so to go from 7 down to 6 is an order of magnitude, a 10-fold increase in the H plus ions. So we have a number of things indicated there. Gastric juices tend to be quite acidic. There is HCl present. It's not as strong as a 1 molar HCl solution that we see down there at pH 0, but it is quite strong. Cola drinks tend to be a little less acidic. Tomatoes, oranges, we see urine has a range. It can be from roughly pH 5 to 7. So depending on diet and physiology of individuals, it'll change a little bit, but it's still, if the urine's down below 5 or up above 7, then you have problems. That can be a clinical diagnosis, is if the urine pH is too high or too low. Notice right above 7, we have the pH of blood, and if the pH of the blood shifts too much from that roughly 7.4, then you get very, very problematic physiology. Proteins can start folding incorrectly and not working, so it's important that the blood stay right at that physiological pH. And then we see we've got baking soda, seawater, milk of magnesia, household ammonia, all those increasing in basicity up to the 1 molar on AOH being 14. You can go below 0, you can go above 14 for the pH scale, but we tend to just focus between those points so that we see that 7 as neutral jumping out at us. Alright, so why do we call it pH? Well, it literally means pouvoir d'hydrogène. It's from the French for power of hydrogen. And it is an equation. The pH equals the negative log of the H3O plus concentration. So if you think back to our learning objectives at the beginning of this lecture, we said that we'd be able to find the pH from the H3O plus concentration, or find the H3O plus concentration from the pH, because we can manipulate that equation to go backward. So therefore you see, if the concentration of H plus is one of those given amounts, it's really the exponent of it, because it's negative log of the H plus. So if we take that exponent, that's the same as taking the negative log, and that's where we get our pHs from 0 to 14. Alright, and now we see again some common substances and their numerical pH. Before it was just on that pH chart at an approximate range, but here we see the actual values, and you see the things that we tend to eat or drink or encounter in our diet. Lemon juice, vinegar, soft drinks, those tend to be acidic. Rainwater is actually acidic because of the carbon dioxide. This is not acid rainwater. That would be much below 5.6, but this is plain old rainwater, just the carbon dioxide in the atmosphere causing it to be slightly acidic. And then we have saliva and so on and so forth. Milk is acidic. People think because it has calcium it's basic. That's not true. Milk is acidic, and if you let your milk go too long, it'll get much more acidic as the bacteria spoil the milk, but ordinarily it should be between 6.3 and 6.6 for pH. Pure water, as we said, should be right at the neutral point, and then blood and egg white, bile, milk of magnesia, washing soda, which is different from baking soda. Washing soda is sodium carbonate, baking soda is sodium hydrogen carbonate, so washing soda is slightly more basic. And then finally sodium hydroxide up at the top of our pH scale. Okay, so if we think back to the Bronsted-Lowry definition of acids and bases, acids are proton donors and bases are proton acceptors. If we look here at HCl giving up an H plus to water would leave behind a Cl minus and also form H3O plus. So if we looked at the reverse reaction, the H3O plus and the Cl minus, we could reform theoretically the HCl and the water by having the Cl minus serve as the proton acceptor and the H3O plus being the proton donor. So we call that conjugate acid, conjugate base chemistry. So because HCl was the parent acid, the Cl minus ion is the conjugate base. Just like water in that example would be the original base, H3O plus would be the conjugate acid. All right, so conjugate acids base pairs differ just by an H plus. The one that's lacking the H plus is now the conjugate base. The one that has an extra H plus is now the conjugate acid. Buffers, as I mentioned earlier in the lecture, buffers are incredibly important to human physiology to keep things how they should be. That's why the blood is pH 7.4, and if it varies much from that at all, we run into problems. Well, buffers work by having a weak acid and its conjugate base. So when small amounts of acid or base are added, the acid will react with the conjugate base to make more of that weak acid instead of decreasing the pH like you might expect when you add acid to a substance. It'll decrease it slightly, but not like in pure water. Likewise, if you added some base, the base would react with the weak acid and form more conjugate base. So you're resisting large pH changes by allowing that weak acid and conjugate base equilibrium to shift instead of having the additional acid cause a large increase in H3O plus concentration or additional base causing a large increase in OH minus concentration. You're keeping it moderate by allowing them to interact with the weak acid or its conjugate base in the buffer. Okay, so looking at that acid rain problem we talked about, it's really the non-metal oxides, which are acidic anhydrides. Because they're present in the air, if they can react with water in the air, they can form acidic solutions, right? They're anhydrides, so if they react with water, they're going to form the acids. Rain with a pH of less than 5.6, we said 5.6 is normal because that's atmospheric carbon dioxide. Extra carbon dioxide, because we've increased the amount of carbon dioxide by all the fossil fuels we've burned, that additional carbon dioxide, more importantly sulfur dioxide, nitrogen monoxide, and nitrogen dioxide, these are the acid anhydrides that give rise to acidic rain, rain that's pH is less than 5.6. And Binghamton is actually an area where acid rain's been a problem. They're sort of where those winds from the Midwest industry have caused a lot of problems in our water. If you look at the Adirondacks, you've got lakes that are essentially dead lakes because very little, if anything, can live in the acid environment from all the acid rain that's fallen. So it's a problem. We have actually done better about it, trying to keep those non-metal oxides out of the atmosphere in the first place, but the problem is far from solved, and it's really an acid-base problem caused by these acid anhydrides, these non-metal oxides. Okay, looking at another case where too much acid is a problem, we have hyperacidity. When the stomach secretes too much acid, that unfortunately is becoming more and more common among people. Antacids are taken, oftentimes to neutralize that excess acid and reduce the symptoms of hyperacidity. A problem with that approach is if you take too much antacid, you can actually increase the pH of blood. We said that pH of blood needs to stay right around that 7.4. So if you're not careful, you might alleviate that hyperacidity, that upset stomach from too much acid. But if you take too much of the antacid, you can end up with alkalosis, and that's the condition where the blood pH is actually too high and blood proteins stop working effectively, and you really need to cut back on your use of antacids so that you don't run into long-term problems from overuse of antacids to solve that hyperacidity problem in the stomach. And here we see a number of different antacids. There's even more today than when this picture was taken, at least different substances that can help with the heartburn from too much acid in the stomach. But this is just a small section of those antacids. Probably the safest ones tend to be the things like the Rolaids or Tums that are largely calcium carbonate. So you're getting some calcium ion, which is generally good for most people, unless you're prone to forming kidney stones or you've already got a large amount of calcium from other sources in your diet. But those tend not to cause that alkalosis as much as the things on the left-hand side, like Phillips milk of magnesia, could do. And so if we look here, we've got a number of the active ingredients, the formula, and then their common name or trade name in the case of the antacids. So baking soda is actually a nice antacid. If you can tolerate it, as we said, it's basic, so it's going to be bitter tasting, but a lot of people will just put, a tablespoon of baking soda into a cup of water, stir it up, and drink it down, and as long as they can tolerate that bitter taste, then it's probably a good approach. At least it's a very inexpensive approach, as long as you don't take too much. Calcium carbonate, that's one I mentioned from Tums. That's a good one because it's really only will react with the excess acid. It won't go too far beyond that to cause that alkalosis, and it gives you extra calcium, which most of us need in our diet. It's a bit chalky tasting, and Tums typically have flavors, either citrus flavors or mint flavors to mask that, but it's chalk, and so it's going to taste chalky. Aluminum hydroxide, that's Amphigel, and then finally magnesium hydroxide, good old milk of magnesia, and those two, as I mentioned, you have to be careful about taking too much of those in particular. Okay, now here we see a different approach, the more typical approach actually nowadays, if you look in the antacid aisle, is not to neutralize the acid with those bases, but rather to try to prevent the problem in the first place. If the stomach is producing too much acid, these acid reducers like Zantac and Tagamet, these are substances that actually decrease the amount of acid the stomach produces in the first place, rather than just masking the problem. So these tend not to have the problem of the alkalosis, the too much base in the blood, because they attack the problem in a different way. So these have far replaced antacids for people who have the chronic condition of too much acid in their stomach. Okay, and just to drive home how important a chapter this chapter 7 on acids and bases is, if you think about the utility of acids, sulfuric acid is the leading chemical substance produced in the United States. That's not a small statement. That's huge. It's incredible how many students will take an introductory course in chemistry and not have any idea about the everyday applications of chemistry. Sulfuric acid is useful for lots and lots of different things. It's used to manufacture fertilizers and industrial chemicals. It's used in, as I said before, automotive batteries. For those of us who have conventional cars, they have lead acid batteries that use sulfuric acid. We make about 40 billion kilograms per year of sulfuric acid, so it is a very important substance. It can be dangerous if it's not used appropriately, but it's a very useful substance in all those different areas because it's a strong acid that does a very predictable chemistry and very valuable chemistry. So we shouldn't be afraid of it just because it's a strong acid, but we do have to treat it with care because it can cause problems. You should never throw a lead acid battery just out on the side of the road or dispose of it in a garbage bag or any of that, because not only do you have the sulfuric acid, you also have the lead. That's an environmental problem. So as long as we use things appropriately and dispose of things appropriately and recycle when we can, then it's no problem to use something that has potentials of harm. But sulfuric acid, despite its potential harm being a strong acid, it's very, very useful and necessary for a lot of the things we do in our modern life. Looking at another acid, hydrochloric acid is another very useful acid. It goes by some other names, as we'll see, but it's a great rust remover. It's very commonly used in toilet bowl cleaners to remove rust or lime stains. It removes lime from mortar and household plumbing fixtures. So just be careful. It is a strong acid, and it will work on things if you're not cautious with it. But in particular for mortar, for removing things like that, you can buy it at a hardware store as muriatic acid. They don't typically call it hydrochloric acid. They call it muriatic acid. But that's what it is. Treat it appropriately, wear gloves, do it only in a well-ventilated area. Never mix it with ammonia-based cleaners, so be careful if you're using it as a toilet bowl cleaner. Use it after you've thoroughly cleaned and rinsed if you've used an ammonia-based cleaner beforehand, but it really does a fantastic job in cleaning, especially those of us who have hard water in our homes. You get a lot of lime scale and rust deposits, and hydrochloric acid is fantastic for removing those. Annual U.S. production is about 4 billion kilograms, so not as much as sulfuric acid, but it's a very, very versatile and important chemical. So we've looked at a couple important acids. Let's look at a base here. Lime, calcium hydroxide, is produced by heating limestone, so driving off a carbon dioxide molecule by adding lots of heat, and that gives us calcium oxide, which we've already defined as lime. If you think back several slides, we showed that lime is actually a basic anhydride. If we add water to it, we can make calcium hydroxide, what we defined as a strong base, although I qualified that to say it's really only a moderate base, but we lumped it so that we had 6 strong acids and then 6 strong bases. Slaked lime is used to make mortar and cement, to sweeten soil, not so that we would eat it, of course, but so that it's more appropriate for plant life. That's what that term means. And here we have 22 billion kilograms per year in the U.S. So remember, sulfuric acid was 40 billion. The hydrochloric acid was just a tenth of that at 4 billion. Lime is about half as much produced as sulfuric acid, so it's definitely a very useful substance and a very commonly produced and used substance in U.S. chemistry. And so here we see that process of sweetening soil by adding the slaked lime, the calcium hydroxide. The person should probably have some gloves on, maybe some eye protection. We can't quite see if he has that or not, but it's not especially caustic if you get it on yourself. It's not like sodium hydroxide or potassium hydroxide, for instance, but it is something that you should be careful with. And we see here it's added directly onto the plants, and then as the rain falls, it gets amended to the soil to adjust pH. A lot of plants are pH dependent. If you've ever grown hydrangeas, you might know that the pH will change the color of your hydrangea from pink to blue flowers depending on the pH of the soil. You could add slaked lime to cause that effect too if you happen to want to change the color of hydrangea you're getting and your soil is too acidic. Alright, another common base, sodium hydroxide, also known as lye. Lye is a generic term for sodium or potassium hydroxide, and it can be used as an oven cleaner, drain cleaner. If anyone's watched the movie Fight Club, they use lye to make soap, and people in the U.S. used to make their own soap when we were a more farming country, but nowadays people tend to just buy soap. So it tends to be only commercially used to make soap, but you could make soap at home as long as you're careful and you know what you're doing. And this one's another important chemical. U.S. production of 9 billion kilograms per year, so a little more than twice as much as our hydrochloric acid is our sodium hydroxide. Ammonia, a weak base, is another important industrial chemical. It's used as a fertilizer and in household cleaning products. Annual U.S. production about 11 billion kilograms. It was a long time before we figured out how to make ammonia. Fritz Haber, the Haber process, is what allowed us to fix nitrogen, to take nitrogen from the air and make it into ammonia. And that allowed for the Industrial Revolution. It allowed for all of these large amounts of fertilizers to have rapid growth of plants and enough plants to feed a growing population. It also prolonged World War I because Haber was working for the Germans. He was a German, and he figured this out. The Allies tried to cut off the source of fertilizer to Germany, which was bat guano from Argentina, and so that was a way to sort of force the war over more quickly. But once Haber discovered the process for making ammonia, he was able to have artificial fertilizers, and the war unfortunately dragged on as a result. Haber also created a method for making chlorine gas that was used as a war gas against the Allies. So unfortunately, that chemist who made some big important contributions also made some contributions that unfortunately extended the war in the case of World War I. Okay, so finally wrapping things all together. Hopefully you've had an interesting time here with acids and bases. They're among the most important topics we talk about in chemistry, especially those of you who are interested in the health sciences. We've already seen some of the medical applications of some acids and bases on these slides and in the text. So concentrated acids and bases are corrosive to tissue and are health hazards. You want to be careful. You want to wear gloves, handle them appropriately. They can denature proteins in living cells, so they can really do a number on the cells if you touch directly with your skin cells or you inhale the vapors in your lung cells, so you have to be very careful. Despite these hazards, the human body has wonderful mechanisms for maintaining proper pH of tissue, blood, and body fluids, and if we avoid doing things that are disruptive to that, like we mentioned with the alkalosis, if you take too many antacids of certain types, that can affect blood pH. So as long as we don't do much to actively disrupt it, the body is well equipped to maintain pH by a lot of buffer systems that are actively used by the body to minimize pH changes with acid or base increases. So hopefully you've enjoyed this chapter on acid and base chemistry, and we'll be ready to talk again for the next chapter.